which is a measure of the separation of charge in a bond gives rise to a dipole moment, which is a measure of the polarity of the bond. Now, it is important to remember that dipole moments are actually vectors, and as a consequence, they have both magnitude and direction. So let's take a look at the case for carbon dioxide, or CO2, which we've drawn here. We can see that the bonds in CO2 are actually polar because oxygen is more electronegative than carbon. And here we've actually drawn the dipole moments above each of the bonds in CO2. We can see that the individual dipole moments in CO2 lie in equal and opposite directions, and therefore the dipole moments cancel. As a consequence, there is no net dipole moment in CO2, and the molecule is therefore nonpolar. Let's contrast that with the case for water, or H2O, which we've shown here. Again, we can see that the individual bonds in water are polar because oxygen is more electronegative than hydrogen. And again, we've actually drawn the dipole moments in water. Now let's redraw this dipole moment over here, and we'll redraw the other dipole moment over here. We can see that water is a little bit more complicated because the dipole moments in water lie along an angle. However, what we can do is separate the individual contributions. So we're going to take this dipole moment and separate it into the contribution in the x direction, or horizontal direction, and a contribution in the y, or vertical direction. And we can do exactly the same thing for the other dipole moment, separating the contribution in the x, or horizontal direction, and the y, or vertical direction. What we can see is that the dipole moments along the x direction again lie in equal and opposite directions, and therefore the x directions cancel. However, the contributions in the y direction lie in the same direction, and therefore we can write a net dipole moment in this direction. And the molecule therefore has a net dipole moment, and we can classify the molecule as being polar. Now, in summary, diatomic molecules with polar covalent bonds have a dipole moment and are therefore polar. However, in polyatomic molecules, the presence or absence of a dipole moment depends on the structure of the molecule. For molecules that are very symmetrical, the individual dipole moments can cancel each other, giving a net dipole moment of 0. It's important to remember that the shape of a molecule plays an important role in determining the polarity of the molecule. In a bond containing atoms with different electronegativities, the electrons are shared unequally, which gives rise to a dipole moment. If the individual dipole moments in a molecule do not cancel, then a net dipole moment for the molecule results, and the molecule becomes polar. So here we have the case of carbon dioxide, which is nonpolar because the individual dipole moments cancel, and the case of water, which has a net dipole moment and gives rise to a polar molecule. Here we will learn how to predict the polarities of various molecules using the examples of carbon dioxide and water. On the left we have the Lewis structure for CO2, and we can see here that it should have the Vesper class AX2, indicating that the molecule will be linear. Looking at the atoms within the bonds, we see that oxygen is more electronegative than carbon. This will result in a separation of charge, making the bonds within CO2 polar. We indicate this by drawing a dipole moment, where the head of the arrow points in the direction of the more electronegative elements. We also draw a vertical line at the more electropositive element, creating what kind of looks like a positive sign. So it's important to remember that dipole moments are vectors, meaning that they have both magnitude and direction. And so we can see here that although the individual bonds within carbon dioxide are polar, indicated by the two dipole moments, those dipole moments are in equal and opposite directions. So although the bonds within CO2 are both polar, they cancel because they are in equal and opposite directions. And so as a whole, the molecule overall is nonpolar, as indicated here. Next, looking at the example of water, we see that we've drawn the Lewis structure for H2O on the right, and it should have the Vesper class AX2E2, which results in a molecule that has a shape that is bent, as we've drawn here. Again, looking at the electronegativities of oxygen and hydrogen, we see that oxygen is more electronegative than hydrogen, and so we would draw a dipole moment with the head of the arrow pointing towards oxygen, which is the more electronegative element. Now, in this case, the dipole moments are drawn at an angle, but we can separate out the contributions from the horizontal component of the dipole moment and the vertical contributions to the dipole moment. And we can see here that once again the horizontal components are in equal and opposite directions and they cancel. However, the vertical components lie in the same direction and they are additive, and this results in a net dipole moment for the molecule, which points in this direction, going from hydrogen to oxygen. As a consequence, because of this net dipole moment, the molecule is polar. Now, in some cases, you might notice on the internet that the dipole moments are drawn in the opposite direction. And this is the convention used in the United Kingdom, where the head of the arrow is pointed in the direction of the more electropositive element. You can see that the difference between these two conventions, United Kingdom and North America, is that in North America, the head of the arrow points in the more electronegative element, and we have a vertical line at the more electropositive element, which looks like a positive sign. In the UK, there's no vertical line at the tail of the arrow, and the head of the arrow points in the more electropositive element. So how can you tell whether or not a molecule is polar? The analogy we can use is one of a tug of war. In this case, we have two people, both equally strong, pulling the rope in opposite directions. In this case, nobody wins and the molecule would be nonpolar. Here we have a molecule with 3 atoms, which we represent as 3 people in a tug of war. So we can see that the team with 2 people will be stronger or have a greater effect than the team with 1 person, and therefore the molecule is polar. Here we have a 3-way tug of war using 3 equally strong people, and in this case they all pull in opposite directions and the molecule would be polar. Here we have another tug of war, but in this case one of the teams has 2 people, and therefore this team would win and the molecule would be polar. Here we have another 3-way tug of war, where in this case the 2 teams on the bottom are stronger than the team on the top, and they would win, and so the molecule would be polar.